All right, in this video, we're going to go over the substitution method for integration. All right, so when do we use the substitution method? Well, the substitution method for integration is used when the integrand, the thing in our integral, is the result of a chain rule. So this is integration's answer to chain rule. All right, and so the substitution rule says this. It says, suppose you want to integrate f of g of x times g prime of x with respect to x, dx. We know, hopefully you're comfortable knowing that that is a chain rule. So what do? What we do is we perform a substitution. It's called U-Substitution, in fact. And we're going to sub in u and du such that now the integral, instead of looking like a chain rule, now it becomes just our generic f of u du. So that now we can integrate it and we get big F of u plus c. I probably should have chose different letters now that I look at this. All right, so the goal is to perform a substitution using u and du such that the integral becomes easier to evaluate. You can only substitute if everything matches up exactly. That's a very important part that you get out of this, okay? All right, so this is what's going to happen, folks. We're going to do a bunch of examples. Do not be frustrated. I do not expect you to understand this after maybe the first couple examples, but towards the end of the video, I'm hoping that you guys will see the pattern. All right, here we go. So for example, we have the integral of 3x squared times x cubed minus 3 to the second power dx. Okay, so why do we have to use the substitution rule? Is because the only other way we know how to go about this is that we would have to multiply x cubed minus 3 by itself 2 times, and then distribute a 3x squared to that product, and then integrate each term by term. We're not going to do all that. Instead, we're going to do U-Substitution. All right, so U-Substitution says this. We need to identify a u, and we need to calculate a du. Okay, so what is du? Du is literally, well, not literally, it is. It's the derivative of whatever you say u is. Okay, so that's kind of the motivating factor that goes behind how you identify what you should let your u equal. You need both u and you also need du to be in your integral when you do the substitution. And actually, du needs to be up to a constant multiple. We'll talk about that in a few minutes. All right, so as far as u, start with u. How do you know what to let u equal? Well, you have two options for u. U can either be 3x squared or u could be x cubed minus 3. Well, how do I know which one should be u? Keep in mind, I also need the derivative of u to be in my integrand. That's the key. Du is really the key. So for that reasoning, u is x cubed minus 3. Why is that? Because du has to be the derivative of that. What's the derivative of x cubed minus 3? It's going to be a 3x squared. And we're going to put our differential dx at the end. This indicates that we took that derivative with respect to x. And yes, it's very important that you put the dx in there. Okay? So that is our correct u and du because now we actually perform the substitution. Okay? So what's the substitution look like? The substitution is, we still have our integral symbol. We have not integrated. But what our substitution tells us is that everywhere we see an x cubed minus 3, we're going to rename it as a u. So everywhere there's an x cubed minus 3, I'm going to call it u. Well, in our integrand, it's u, but it's going to be raised to the second power because that x cubed minus 3 was raised to the second power. So now it becomes u to the second power. Okay? Now, we have subbed out that part. Let me see if I can do this. So that part is now gone. But we're not done with our substitution because we still have a 3x squared dx, which we need to substitute out. And that is precisely what du equals. So the 3x squared dx doesn't disappear. It just simply gets repackaged and called du. All right, like I said, we're going to go through several examples. So that is the substitution. So 3x squared times x cubed minus 3 to the second power dx now becomes, after we do our substitution, it becomes a u squared du. And when you perform substitution, all your variables will be switched out. You'll never have an integral that has both a u and an x. Okay, everything has to be switched over to u. So now this becomes what we covered in the last homework section, in the last video, excuse me. When we integrate u squared, it becomes now, remember we add 1 to the power, it becomes u to the third over 3 plus c, which I like to rewrite as a 1/3 u to the third plus c. But now keep in mind, okay, our final answer has to be in the same variable in which we started off with. Our question asks us a variable in terms of x. Okay, our final answer also has to be in terms of x. So the last step is we have to replace u with its expression in terms of x. We said that u was x cubed minus 3. So then we get 1/3 times x cubed minus 3 to the third power plus c. And there we go, folks. That is our antiderivative. Really quickly, how do we check ourselves? So let's take the derivative of the antiderivative. That sounds weird. And we're going to do that via the chain rule, right? So the 3 comes out front, multiplies the 1/3. We leave the inside alone, but now we raise it to the second power. And then we take the derivative of the inside, which gives us a 3x squared. Right? Derivative of x cubed minus 3 is a 3x squared. And then derivative of any constant plus c is 0. Let's clean this up. 3 times 1/3, they're going to cancel, leave us with a 1. So we're left with x cubed minus 3 to the second power times 3x squared. Remember, the order of multiplication doesn't matter. I could put the 3x squared wherever I want to. And that is precisely what our integrand is. Okay, so you can always check yourself by taking derivatives. Okay, so the key, folks, is select your u, but keep in mind you also need the du in there. So u, for the most part, is going to be the expression that has the higher power, because remember we take the derivative, the x drops down by 1, unless it's an e. Maybe I'll make up one of those in just a second. All right, here we go. For example, evaluate this, the integral of 8x times the square root of 3 plus 4x squared dx. First step before we do anything is we need to rewrite that square root as the 1/2 power. Okay, just rewriting there. All right. Most of the times, folks, the dead giveaway about what should be u is the thing that has the power on it, right? Outside of a parentheses or something like that. This means that u should be a 3 plus 4x squared. Why is that? Because what's the derivative of 3 plus 4x squared? Our du would be an 8x dx. And that matches up inside of our integral. Right? Let me show you, right? Because we have the u and we also have the du that matches up exactly. Let me show you the incorrect substitution really quickly. Maybe that might be helpful. What if you said, okay, I want u to equal 8x. That's fine. What's du? What's the derivative of an 8x? It would be an 8 dx. But we're going to have a problem because we're not able to substitute out the 3 plus 4x squared in that case. So that's how you know you've done an incorrect substitution. Okay? All right. So that being said, let's perform the correct substitution here. So substituting the 3 plus 4x squared to the 1/2 power, that becomes u to the 1/2 power. Okay? So in fact, let me visually show you this. So that's now subbed out, but we still have what visually? Or we still have what left over in the integral? We have an 8x dx. 8x dx gets packaged up because they're multiplying each other, and they're just renamed as du. Okay? Nothing disappears. It's just repackaged and is subbed out and it's called du. All right, so let me just go back and put in this. All right. And so now we perform the integration just like we did last video. We're going to add 1 to the power. So we get u to the 3/2 divided by 3/2 plus c. And as we did in the previous video as well, we're going to rewrite dividing by 3/2 is the same as multiplying something by 2/3. Remember, keep, change, flip. So it's 2/3 u to the 3/2 plus c. And then lastly, we need to replace u with its expression in terms of x, and it was 3 plus 4x squared raised to the 3/2 power plus c. Once again, folks, there's no reason why you should be getting these wrong because all you have to do is take the derivative and see if you get back what's your integrand. All right. So up to now, our differentials, the du stuff, has been matching up exactly with what's been in our integral, right? The previous example, du was 8x dx. We had exactly 8x dx. The first example, du was a 3x squared dx. That's exactly what we had, 3x squared dx. Well, it turns out that this substitution method also works as long as you're able to correct it by multiplying through by a constant. So substitution works up to what we call a constant multiple. Let me show you what I mean. In this example, we got to evaluate 2x cubed x to the 4th minus 5. What I want us to do is, what do you think u should equal? Hopefully you said u equals x to the 4th minus 5. Why is that? Because du is equal to a 4x cubed dx. Remember, du is the derivative of u. Du has nothing to do with your integral as far as how you figure out what that is. Du is simply the derivative of u. Okay? But as we start to do our substitution, we're going to have an issue because we don't have a 4x cubed dx. Instead, what we have is a 2x cubed dx. So what we need to do is we're able to multiply the du equation. We're able to multiply it by a constant. That's allowed. What you cannot do is multiply through by an x or an independent variable. But you are allowed to multiply through by a constant. So the question becomes, in order for me to complete the substitution, I need the 4x cubed in my work over here. I need it to become a 2x cubed dx. Well, what do you multiply 4 by to turn it into a 2? Well, it should be, hopefully you said a 1/2. So 1/2 times 4 gets you to the 2x cubed. And so that's what we're going to do here. So I'm going to come down to my du equation. And what we're saying is that if we take 1/2 of du, that's going to equal, because an equation, do it to both sides, that's going to equal 1/2 times 4x cubed dx, which equals a 2x cubed dx. All right. So 1/2 du gets us to what we want, a 2x cubed dx. Now let's substitute. The x to the 4th minus 5, that becomes u to the understood first power. The 2x cubed dx gets replaced, and we're going to call it a 1/2 du. So remember, everything's multiplying. The order of multiplication doesn't matter. So what I'm going to do is I'm going to take that du, put it there. We usually put the du at the end. We always put the du at the end. And then the 1/2, I actually have options. I can put the 1/2 inside my integral, or if I wanted to, through the properties we discussed in the last video, I could take the 1/2 and pull it out here. It makes no difference where you put your 1/2. Okay? All right. I'm just going to move mine on the inside. It makes no difference whatsoever. So now what we get is, now we integrate. Now we get 1 over 2 times u to the 2nd power divided by 2 plus c. Professor Dixon, what happened to your du? Why did it change to a plus c? It did not change to a plus c. If you recall in the previous video, we talked about how the integral sign and du, they are operators. They mean we should do something. After we perform the something, in this case the integration, we drop those symbols. Okay? Just like when I said in the previous video, just like when we do 3 plus 2, plus is an operator. After we do the addition, we drop the sign. So that's why the integral sign and the du drops off. Okay, to clean up this answer, we're going to multiply these. So remember, to multiply fractions, we multiply the numerators. 1 times u squared is u squared over 2 times 2, which is 4, plus c. Last step is to replace u with its value in terms of x, which is x to the 4th minus 5. So my final answer is a 1/4 x to the 4th minus 5 to the 2nd power plus c. All right. Okay, so the key with this one is that our DUs, our differentials, didn't match up exactly. So let me also go over a shortcut on how you can figure out what to multiply both sides of your DU equation by to get the differentials to match up. This is what you do every single time, y'all. To get the correct fraction for your DUs to match up, what you do is you take the coefficient of the differential inside your integral, in this case is 2, and you divide it by the coefficient in the differential of your work, 4. So where do we get 1/2 from? It's going to be 2 divided by 4, which reduces to 1/2. So that's a quick way of doing that. You take the coefficient of the differential in your integral, divide it by the coefficient of the differential in your work. All right, here we go. Kind of go through this one quickly here. So we have that integral. Let's do our U-substitution. Hopefully by now you're super comfortable figuring out what u is. So u is going to be x to the 5th plus 1. What's du? Du should be a 5x to the 4th dx. But we don't have that, do we? Instead, we have a 3x to the 4th dx. Remember, you can only substitute if they match up exactly. So the question becomes, what do I multiply 5 by to turn it into a 3x to the 4th? Well, what was the trick I showed you in the previous question? Is you take 3 and you divide it by 5, and that is our, what I call the corrective constant multiple. So 3/5 du is going to equal 3/5 times 5x to the 4th dx. Well, what is 3/5 times 5x to the 4th? The 5's cancel, and we're left with the 3x to the 4th dx, which is precisely what we want. So 3/5 du is the substitution that we're going to perform here. Here we go. Integral x to the 5th plus 1 to the 2nd power. That becomes u to the 2nd power. The 3x to the 4th dx becomes not just a du, but it becomes a 3/5 du. Okay, don't forget the 3/5. Now we integrate. The 3 over 5 is going to multiply whatever the integral of u squared is, which is u to the 3rd over 3 plus c. We can cross cancel since we're multiplying here, so the 3's cancel. And we're left with the u to the 3rd over 5 times 1, which is 5, plus c. And then the last step is this is going to be a 1/5. I like to write it this way. Replace u with what it was in terms of x. It was x to the 5th plus 1 to the 3rd power plus c. Once again, how do we check ourselves? Take the derivative. All right. Just how many more? Just a few more, I promise. I want to make sure you guys are super prepared. All right, here we go. Ooh, that's an interesting one. What if we have the integral of 10x plus 20 times x squared plus 4x? Ooh-wee. All right. U-substitution. What do we let u equal? Should it be the 10x plus 20 or the x squared plus 4? Keep in mind, we also need du in there. For that reason, u should be the x squared plus 4x. Why is that? That's because du, the derivative of x squared plus 4x, is a 2x plus 4 dx. And I am off, once again, we are off by a constant multiple. What is the multiple that we're off by? We need 2x plus 4 dx to become a 10x plus 20. So the question becomes, what do you multiply 2x plus 4 by to make it into a 10x plus 20? Well, what's our little cheat code? We take 10 and we can divide it by 2. What's 10 divided by 2? 10 divided by 2 is 5. So that's what we need to multiply by. So 5 du is going to equal 5 times 2x plus 4 dx, which we know is, if we distribute, a 10x plus 20 dx. Okay? And yes, for substitution to work, that'll always be the case where it's just one constant multiple that you distribute through. At least in your homework, and at least in this class. All right, so now we substitute. We have the integral of x squared plus 4x to the first power. That becomes u to the first power. Okay, and in fact, I don't even have to write the 1. 10x plus 20 dx becomes not just a du, but becomes 5 du. And now we integrate. So we get 5 times u to the add 1 to the power, divide by the new power, plus c. And lastly, we replace u with x squared plus 4x. So the final answer is 5 halves x squared plus 4x to the second power plus c. All right. Okay, the very last one. Let's evaluate 3x squared plus 1 over 4x cubed plus 4x minus 5. Yuck. All right. First thing we need to realize is that that entire denominator is raised to an understood first power. So our first step is to rewrite this integral as, okay, make sure you do parentheses here, the numerator 3x squared plus 1 gets multiplied by 4x cubed plus 4x minus 5 to the negative 1 power. Remember, we bring up the factor, we take the opposite sign of the exponent of the power. Now, that negative 1 power is a dead giveaway. Now that means that, look, for this to work, u has to be the 4x cubed plus 4x plus 5. Or minus 5, excuse me. Which indicates that du is a 12x squared plus 4 dx. Remember, du is the derivative of whatever you say u is. All right, do we match up exactly? Do the differentials match up exactly? They do not. Okay, so what do? To figure out the constant that we should multiply through by, we take 3 and we divide it by 12. Or you could say 1 divided by 4. So 3 divided by 12 or 1 divided by 4, they're the same thing. It's a 1/4. Right? So that's our constant multiple we should introduce. 1/4 du is going to equal 1/4 times 12x squared plus 4 dx. And if we are to distribute the 1/4, which is dividing by 4, you get 3x squared plus 1 dx. So 1/4 du is going to be our substitution when we do the differentials. So here we go. This will be the integral of the 4x cubed stuff. That's u to the negative 1. The 3x squared plus 1 dx, for the reasons we just discussed, is a 1/4 du. And if you recall at the end of the last video, we said negative 1 is a special case because if I try to add 1, I get u to the 0 over 0. So if you remember, we said when your powers are negative 1 and you integrate, it becomes the natural log. So this is 1/4 times the natural log of the absolute value of u plus c. And then we replace u with what it was in terms of x, and it was 4x cubed plus 4x minus 5 plus c. All right. Folks, if you understood that last question, I think you're going to be really solid with your homework. See you guys in the next video.